Hi, my name is Chris, and I am an AE 2610 student. This is my presentation for the Rijke tube experiment. A Rijke tube is an example of a pulse combustor where the intensity of combustion varies in an oscillating pattern. This type of combustor has many different applications, such as in pulse jets. Mixing is more efficient in pulse combustion compared to standard combustion, but the oscillations may not always be desirable. A flame is used to drive resonance within the tube. This occurs when there is a feedback loop between heat, pressure, and velocity waves. The heat from the flame drives the pressure wave, which then drives the velocity wave, which then drives the intensity of the flame. The purpose of this experiment is exploring what factors, such as flame location and tube setup, have an impact on resonance. The impact of resonance on the properties of pressure and heat waves are also determined. These properties include frequency, magnitude, and phase. The Rijke tube in this experiment is 72 inches long and open at both ends. The upper end is vented through the ceiling through an exhaust system. A flame is fueled with propane gas from a tank. A scissor jack is used to vary the position of the flame. The 0-inch flame location is located 18 inches from the bottom of the tube. In addition, a small fan is used to provide an updraft. There are three piezoelectric transducers labeled P1, P2, and P3. They measure pressure inside the tube and give a voltage output. They are equally spaced 18 inches apart at 1/4, 1/2, and 3/4 of the tube. They are not mounted directly to the main tube, but sit inside of their own tube to protect them from heat and shock. There is a photometer tube labeled PMT, which measures intensity of light and therefore the intensity of the flame. It looks into a quartz window at the 0-inch flame location. The output is voltage. All signals are obtained through data acquisition and sent to the computer for analysis. 4 tests were carried out. At 0-inch flame location with the valve closed, 0-inch with the valve open, and 2-inch with the valve closed. A 4th test involved increasing the position steadily until resonance stopped, which occurred at 4.9 inches with the valve closed. For every test, the 3 transducers and the photomultiplier measured RMS voltage, peak frequency, and associated phase. Here are the frequency results. If there is resonance within the tube, the peak frequency is measured to be 97 Hz. Otherwise, if there is no resonance, there is no peak frequency, and the frequency is reported as 1 Hz. Therefore, the presence of peak frequency is a reliable way to determine the presence of resonance if there is a good estimate of peak frequency. The PMT frequency is only reliable for the 0-inch location, since the flame moves away, but the PMT does not move alongside the flame. To calculate estimated frequency, first the speed of sound is calculated from gamma, ambient air temperature, and R gas constant for air. Then the frequency can be determined. It is close to the experimental frequency. Here are the voltage and amplitude results. The voltage measurements from the 3 transducers are converted to decibels. First, voltage is converted to pressure RMS using a calibration curve from the chart shown on the left. An approximation involved dividing the millivolt measurement by 95. From here, pressure RMS and pressure RMS at the threshold of hearing is used to obtain decibels. The presence of resonance tends to increase the amplitude of the signal. This effect is seen by measurements in P1 and P3, but it is not prominent in measurements by P2. The flame intensity measurement decreases with increasing position, since the flame is moving away from the multiplier. Opening the valve also decreases the intensity of the flame. Here's the phase data. The phase data was first normalized so that P2 has a measurement of 0 degrees. This involves subtracting all phase measurements by the measurement from P2. One thing to note is that the pressure signal lags behind the flame signal by about 90 degrees. P1, P2, and P3 do not vary by each other very much. In conclusion, it is determined that resonance requires a vertical closed tube, an updraft of air, with a heat source located near the bottom. Otherwise, for example, if the valve is open or the flame is located in the middle, there is no resonance. The presence of resonance is indicated by a distinct peak frequency and an increase in amplitude. The pressure wave tends to lag behind the heat wave by about 90 degrees.